Hi guys, my name is Atul and I welcome you all on my new video on iron-carbide phase diagram. Now, the first question arises in my mind is that why we need to study iron-carbide phase diagram. Okay. If we are having knowledge and deep understanding of phase diagrams, then it is very easy and convenient way to design and control the heat treatment processes. First is heat treatment processes. The second one, as a mechanical engineer, we all interested in mechanical properties of any component, and that mechanical properties of component came from the microstructure of that component. Second one is microstructure, and that microstructure is derived from the heat treatment. Okay. Consequently, iron-carbide phase diagram derives the physical or mechanical properties of component. Now, second question, why iron-carbide? We are using almost 70 to 80% of steel components, and steel is an alloy of iron and carbon, and with other alloying elements like silicon, sulfur, chromium, nickel, cobalt, etc. But considering all these elements at a time and representing them on phase diagram is very complicated and extremely difficult to understand. That's why we have taken only iron and carbon. So our system comprises of binary system now. That means we are having only two components. Okay. So what kind of alloy is a steel? Its combination actually, when steel is alloyed with or iron alloyed with carbon, forms a interstitial. That means carbon is not replacing the iron atom, not replacing iron. That is interstitial. That means carbon is getting fitted in iron where there is an empty space in the crystal lattice of iron. If we are going further, like nickel and chromium, iron, if we are mixing with nickel, then it is a substitutional type of alloy. Okay, but here we are much interested in iron and carbon only. So we will discuss that only. Now there will be a space constraint to get the carbon dissolved into iron, and the maximum percentage of iron can get dissolved into the maximum percentage of carbon get dissolved into iron is 67%, 0.67 percentage approximately, I'm telling you. Okay, now without wasting our time here much we'll go to the real iron carbide diagram. There I will explain you in detail everything. After watching this video, you will be able to schematically draw the iron carbide phase diagram, label the different regions, and you can identify their composition and the phases present and mass fraction of that. And most important, you will be able to write the three phase reactions transformation, that is eutectic, eutectoid and peritectic transformation. Before start of drawing the iron carbide diagram, I want to know you what is in my liquidous line and solidus line. Here in diagram I have taken two components which are having two different melting points. Okay, here in this region both the component or element having in solid state, but above this region both the element is in liquid state, but in between this region one is in liquid state and one is in solid state. So what is my liquidous line? Liquidous line is the line above which component or element is in liquid state, and solidus line is the below which component or element is in solid state. Okay, and I want to tell you some names that we are going to discuss in iron carbide diagram. First one is the ferrite. What? Ferrite. Ferrite is a pure form of iron. That is Fe. Then alpha ferrite. Just name at room temperature we are calling that pure form of ferrite is or iron is alpha ferrite. Then gamma ferrite or austenite, we will call that as austenite at elevated temperature above 723 degrees Celsius. We will call that pure form of iron as a gamma austenite, which is having FCC crystal structure. Alpha ferrite is having BCC crystal structure. I will tell you that once again when I am going to explain you the diagram. Then delta ferrite. This is also having BCC crystal structure, but at elevated temperature of just a second, I will check and tell you. Of above 1400 Celsius. Okay. Then fifth cementite. Now we are saying that carbon is getting dissolved into iron, but when it gets dissolved, it forms a compound with iron, that is Fe3C, that we call in metallurgical language as a cementite, which is very hard and brittle. Then the last one is the ledoburite, which is a mixture of gamma austenite or gamma iron plus cementite. Okay. Now we will move on to schematic representation of iron-carbide phase diagram. Schematic representation of iron-carbide phase diagram. Here I have chosen a already drawn phase diagram so that instead of drawing now and wasting time on it, I will explain it bit more so that you will understand clearly. On x-axis, I have taken weight percentage of carbon. On y-axis, it is a it is at temperature in degrees Celsius. The extreme right-hand vertical line indicates the maximum solubility of carbon or solubility limit of carbon in iron, which is 6.67%. Okay, now we will start. First of all, we will take the pure form of iron called ferrite. We are taking ferrite. Upon heating, it experiences two changes in crystal structure before it melts. Here it is getting melt. If someone asks you or any exam in competitive what is the melting point of pure form of iron, then you have to mention 1539 degrees Celsius. Okay. Now we have taken a pure ferrite that we call that at room temperature alpha iron. What? Alpha iron. This alpha iron is having, I already told you, BCC crystal structure. Okay. Upon heating till 910 degree, it will be alpha iron only. But upon heating the pure form of iron, it will get changed to gamma austenite. This region is a gamma austenite. We are calling that as a gamma iron or gamma austenite. It is a pure form of iron. Upon heating further, it will change again to different crystal structure. Sorry, I have to tell you here, gamma austenite is having FCC crystal structure, face-centered crystal structure. Upon heating further, this FCC will change to again back to BCC. Here it is BCC in this region from 1400 to 1539. This iron we call it as delta. Okay. As we have mentioned this line as a ferrite line, similarly we can mention the extreme right side line as a cementite. That is Fe3C. For pure form of iron, there are three crystal structures available. Upon heating, we will get the three crystal structure. First, at the room temperature, BCC, which is a stable form. Then most widely used, the austenite, which is a FCC crystal structure, and the last one at elevated temperature, which is having BCC crystal structure. Here you have to keep in mind the temperature range from where to where it is having the range. Now I had drawn this weight percentage of carbon up to 6.67%. Until now I had discussed about pure form of iron, that is at 0% of carbon, and at maximum percentage of carbon. What are the different regions available in this intermediate region, and what are the composition of that, and what are the names, which names we are using to call them? We will study that one by one. As a carbon is an interstitial impurity in iron and get dissolved with each of ferrites like alpha iron, gamma iron or gamma austenites, or delta iron. Now we will dissolve carbon in alpha iron or in alpha BCC ferrites. You can see here, this is the region of alpha iron, which is having maximum of 0.02% of carbon dissolvability. Because of this, means very less carbon is getting dissolved in alpha ferrite. This is very soft compared to other steels and may be in magnetic nature. Now we will dissolve carbon in gamma austenite, which is having FCC crystal structure. From figure, the maximum of 2.1, because if you see, this is the region. I will draw it for your what region gamma austenite is existing. This is the region in which gamma austenite is available. So the maximum solubility of carbon in gamma austenite is 2.1. Now you can question like why there is a difference in solubility of carbon in alpha and gamma ferrite. The answer is very simple. In BCC there is not enough space for carbon, but in FCC crystallographic structure there is some extra space to get it dissolved into iron. Phase transformation of austenite steel is very important because mostly the steels which we are using is austenite, and for the same steel we will go for heat treatment. So here take a note of temperature for which phase transformation occurs. That means this temperature range. Okay. In any interview or any competitive exam, you need to understand or remember this curve, because for pure form of gamma austenite, this is the transformation temperature, and this is the lowest transformation temperature for gamma austenite. Then again, once the carbon percentage is increasing, it will temperature also increase, the transformation temperature I am talking about. Now next comes the delta ferrite, this region. Okay, I will say this region. Here you can see the maximum percentage of carbon is increased, though it is having BCC crystal structure of same like alpha ferrite. This is because at high temperature the carbon solubility will increase. That's why we will get a little bit more carbon percentage to get it dissolved into the iron. As earlier I had told you that for pure form of iron, this is the melting point. That means above this line there will be a liquid region. This is liquid region, and this line is liquidous line. Okay, this line here, as delta ferrite and alpha ferrite is having same properties, but delta ferrite is stable at only high temperature range. You can see 1500 to 1400 degrees Celsius. That means it don't have any technological importance, so that we will not going to discuss further more on the delta ferrite. Till now we have discussed about single phase regions. Now we will go further to discuss about two phase regions. Before that, I will just want to repeat what we had discussed here. What are the different names, so that you will identify the regions by yourself and name them. First we have discussed ferrite, that is pure form of iron. Alpha ferrite, we are discussing that now from last 5-10 minutes. Gamma austenite, delta ferrite, cementite, which is a component of Fe3C, and lead burite, this one. And here I missed one, sorry, that is perlite. Sorry, that perlite. Perlite is a mixture of alpha ferrite plus cementite. Now, as you are familiar with these names, now I am going to name the regions which are available in our iron-carbide phase diagrams. First, we will start from delta iron, this region. Okay. Now, this side liquid is there, this side delta is there. So in between this, there will be a liquid plus delta. Okay. Now for this region, this side delta is there and this side gamma austenite is there. So in binary phase, this will be a delta plus gamma austenite. Okay. Now for this region, we will go for naming this region. This side liquid, this side gamma austenite. So this will be liquid plus gamma austenite. Now for this region we are going to name it this region only, because this region we are already named. This region, this side gamma austenite and this side alpha ferrite. So this will be alpha plus gamma Now for this region, means this and up to this. Sorry, I will try one more time. This region. Okay. Here alpha is there and gamma alternate is there, but at room temperature it will form a compound what we call perlite. What is perlite? Is the alpha ferrite plus cementite. This is alpha ferrite plus cementite. Okay. Similarly, we will name the others also. Sorry, by mistake, I had taken this. This region will be a perlite plus alpha ferrite. This region, this will be a perlite plus cementite. This region, cementite plus perlite plus transformed leduburite. This here is 4.3%. Okay, I have overwritten that. This will be a cementite plus leduburite. This will be this one, austenite plus leduburite plus cementite. This region, leduburite plus cementite. Actually, this whole complete region is having single composition, and if you are naming this region, this will be a, because here this side liquid and this side is the cementite. This is cementite region, so this will be a liquid plus cementite. Now we will discuss about important reactions or transformations that occurs in the diagram. Those transformations are having specific temperatures and weight percentage of carbon. First one, we'll discuss about peritectic transformation. For your clearly identifying, I will just change the pen. Yeah. So peritectic transformation occurs at this point. This point is having 0.1% of carbon and temperature of around 1500. So if we are writing down these reactions or transformations, this will be like this. First one is a peritectic. Peritectic peritectic, sorry. Liquid ion plus delta ion on cooling changes to gamma austenite. On heating the gamma austenite, it will change to liquid plus delta ion. This reaction occurs at 1493 degrees Celsius and weight percentage of carbon is 0.1. The second important transformation is ectectoid. I'll just show you where is that ectectoid point. This is the ectectoid point. From here, one solid is changing to perlite plus cementite at this temperature range and 0.8% of carbon. And the third important transformation is eutectic. This is eutectoid. This is peritectic. Peritectic and eutectic. This is eutectic. This is eutectic. Here one liquid transforms to two solid. One is austenite plus ladybirite plus cementite and ladybirite plus cementite. Suppose you forgot those three transformations and their names. An easy way I will tell you that remember how many horizontal lines are there. This is the one, this is the one, and here is also horizontal line. So understand from that transformations occurs at isothermally. So 3 horizontal lines, 3 reactions, 3 transformations. From the carbon content and the reaction or transformation names, we have named some regions of steels. I will mention here. From this point to 0.8% for gamma austenite, the eutectoid reaction is happening. We call it as a hypoeutectoid. Okay, and this up to this region is hypereutectoid. Here, in this point, eutectic reaction is happening. So, at 4.3 and below 4.3 to 2.1, hypereutectic region. Hypereutectic, and 4.3 to 6.7 is, sorry, this is hyper, no, mistakenly hyper. This is hypereutectic, and this is hyper, sorry, my mistake. And already you have known that this region, I will change the pen, okay, up to 2.1 we consider it as a steel, and from 2.1 to 6.67 is a cast iron. Okay. Okay guys, thanks for watching this video. If you like this video, then please like it and don't forget to subscribe. Thank you.